Now it's my pleasure to introduce Julien Guyon, one of the contributors to our last discussion. He's at Bloomberg, and he is going to say that volatility is almost 100% path dependent, with which I strongly agree, by the way.
That's a good start for the talk. Am I allowed? Yeah. You hear me well? Okay, perfect. Hi, everyone. First, thank you very much to the organizers. I'd like to honor the memory of Peter in this way. It's great to be here. And so hello to everyone who is attending in person, and also for everyone who is attending remotely. And it's a great moment to share memories with Peter. The time is short for the talk, so I will just mention one anecdote about Peter that I think defines very well one aspect of his personality, which was, a fantastic personality. But this one I think is amazing. Is I remember, I think it was 2017 in Barcelona. I was giving this full day workshop together with my friend Pierre-Henri Laborde. That was, based on that book, Nonlinear Option Pricing. So, quite new stuff in quant finance. And usually it's the attendees are people in their late 20s, early 30s that are sent by their employer for, training in new stuff. And so we see all those people arrive in the morning, 9 a.m. And then the last one of them was actually Peter, sitting among all of those, and for 7 or 8 hours, and with his pen, always had the pen and always taking notes, paper. And it was fantastic to just see him. He probably did that all the time with also many other people and so it's just fantastic to that's the reason why for me I still cannot believe that Peter passed away and is not here anymore, because he was so young, just always trying to learn everything every day. And that's so thank you to the organizer, and thank you, Peter, for showing us the way of staying young by trying to learn everything, to learn something every day, and being curious for your whole life. And it's that's the one memory that I will take from Peter. This is a talk also kind of honoring the memory of Peter, because that's a talk about volatility modeling. And I had plenty of fantastic discussions with Peter, probably many of you, and especially on volatility modeling. So yeah, I hope that Peter would have liked this talk. That's also and I need to mention another person here, which is Jordan Lequefac, because this is my co-author on that work, and he used to be our intern at Bloomberg, and is now a PhD candidate at Berkeley, California, and is also a Bloomberg PhD fellow from this year. We started this new quant finance PhD fellowship this year. Okay, so you see the title is here. Volatility is mostly path dependent. Okay, so it's going to be again really about volatility modeling and path dependency. So the outline of the talk is here. First, why path dependent volatility? Okay. Why do we consider it? 2, is volatility path dependent? The answer was in the title. And how much of it and how? And then I will turn to the continuous time version of our empirical path dependent volatility model. So this is a quick definition of path dependent volatility. For simplicity, I take zero rates, repo, dividends. Okay, so you have an asset, think for instance of the S&P index. Okay, S, and the volatility is sigma, and you see that sigma is a function of all the past asset prices. Okay, so we all know that the volatility sigma drives the dynamics of S, but there is a feedback loop from prices to volatility, right? So S also drives sigma, because sigma is actually a function of all the past asset prices. So it's a pure feedback model, where volatility, you see, is a completely endogenous factor. It's completely a function of the asset prices. So I mentioned briefly some of the main references in the past decades. So there's the whole Garch literature in econometrics. There is the derivatives approach, so it's more like macro, and it's about pricing models and calibration. So it started with Hobson and Rogers in '98. There was also a continuation of papers after Hobson and Rogers. I myself contributed with this 2014 paper in Risk Magazine, path dependent volatility. There's the econophysics papers from the 2000s, 2010, So it's more a micro point of view. Okay, so it's more microstructure and statistical properties. Somehow we will be more into that category today. And there are recent models with a PDV component. So one by Jim here and Mathieu Rosenbaum and Paul Jusselin, and the recent one also by Léo Parent that I will mention. So there's of course like already quite a lot on path-dependent volatility, but I want to convince you and go like one step further. So this is just like the paper by Hobson and Rogers in Math Finance 98, the one in the Risk Magazine 2014. Okay, so let's start with why path-dependent volatility. I'll go maybe quite fast on some of those slides because I want to be able to show you like the rest of the dots up there. Of course, there's the philosophical argument that the arrow of time goes only one direction. Okay, so the available information is present and the past. Okay, so when we look only at present, that's the Markovian assumption. But it's often made just for simplicity, right? And it's not a fundamental property. So for instance, you may decide that the price of an option at time t depends just on time t and the current price of the asset. But actually, often the present does not capture all the information from the past. And actually, you may want to see the price as a function of current time t and all the past asset prices, right? So there's this intuitive argument, and I like to present it as a small, simple quiz. So for instance, imagine to today, June 3rd, 2022, say the SPX is around 4,000. And now I tell you that 1 year from now, 2023, it's going to be 5,400. What is your best guess for the VIX? Okay, the volatility index. So you see, so 4,000 to 5,400 in 1 year. So market went up. So maybe you say, we know that in that case, volatility should be quite low. So you can say, okay, maybe the VIX would be around 12, 13, quite a low value. But now I add an extra piece of information, which is that 1 month before June 3rd, 2023, which is May 3rd, 2023, which is my birthday, by the way, the S&P is 6,000. Do you update your best guess of the VIX? Of course, because you see that in 1 month, the S&P would have lost 10%. Okay, so it's a little bit like today. So you see that it means that the VIX should probably be much higher than your first estimate was made to as. So maybe the VIX would be, I don't know, 25 or something like that, or 30, but you would certainly update your VIX. And you see, that's exactly path-dependent volatility, because you need to take into account the past values of the asset price. This is a figure showing you the VIX versus the S&P on the x-axis, just to show you that the volatility is clearly not just a function of the current asset value, but it's more complicated, right? For a given S&P value, you can have plenty of different values of the VIX. Actually, you see what happens is that typically you have the S&P, for instance, going up, and then the volatility goes down. And then at some point, the S&P goes down a lot, and then the VIX shoots up. And then it starts again sliding, again that slope. And this is, for instance, like examples where the S&P up goes down, then that shoots up the volatility, and then it starts again to be more like a function of it. So it's kind of, you see the volatility restrikes regularly, but kind of continuously. And that's exactly what path-dependent volatility models can do. There's the financial and scaling argument, which is important, which is that according to me, in this problem of modeling prices of assets, the two basic quantities that possess a natural scale are the volatility levels and the asset returns, right? So it's clear that asset levels do not mean anything, right? The S&P can be like 500 or it can be 5,000. There's no problem, but it's not the case for the volatility, right? Volatility somehow stays always between, I don't know, 10% and 80%, for instance, when you look at the VIX, whatever the value of the S&P. So a good model should actually relate those two quantities. And so when you look at local volatility model, for instance, it links the volatility level to the asset level. Okay. But the asset level does not mean really anything. So that does not really make any financial sense. So that's the reason why well-chosen PDV models need not be recalibrated as often as the local vol model. You also have the family of stochastic volatility models, and then they connect the volatility return to the asset return, okay? And that's better, that works much better. But the fact is volatility, only very high level of vol, okay, will allow for the large movements of volatility that we see in the market. And so vol is actually can be extremely non-constant, and typically a large mean reversion is added to keep volatility within its natural range. So I just realized here that that's the old version of the slides that I see here. So there, I will correct something because that's not the latest version of the slide that I see. It's fine. So by contrast, the PDV models, that directly links the past returns to the current level of volatility can naturally capture those large changes in volatility and while maintaining volatility in its natural range. Okay. So that's basically the summary in this table. So this stochastic volatility it's quite good models, but what exactly is the relationship between stochastic volatility and path-dependent volatility? So let's take the example of a simple stochastic volatility model, one factor here. So we have two independent Brownian motion, W and W perp, if you want here, and this constant correlation rho. Okay. So you see that in the case where rho is equal to, so you see like the dW here, it can be rewritten as ds over s, and you have to multiply by 1 over a, which is the instantaneous, the stochastic volatility, right? A is the stochastic volatility here. So we see that if rho is equal to 0, then actually the volatility process is completely autonomous, okay? And the stochastic volatility is strictly path independent, right? There's nothing. So the asset price is a complete slave process that has absolutely no feedback on volatility. Volatility lives completely by itself. Now, in the case where rho is not 0 and not also minus or plus 1, then you see that you have a partial feedback from asset price to volatility, okay? Because you can write, you see here that I do have a pointer here. So you see here like this ds over s is like information from the past asset returns, okay? And so you have a partial feedback here, and there's an independent part that is here. And in the case where rho is plus or minus 1, actually it's completely, it's a pure feedback. So the stochastic volatility is fully path dependent, okay? But the path dependent, you see here like those function f and g, you can write in that case the instantaneous vol as just a function of the past asset return, but it's a very complicated and not explicit function, right? Because you have to multiply by 1 over AU. What is AU? AU is the same thing here, but written at time u and so on and so forth. Okay, so it's not an explicit function. So you can't really choose how it's how the path dependent volatility function exactly is. And another argument in favor of path-dependent volatility is when you try to jointly calibrate stochastic volatility model to S&P and VIX smiles, okay, which I've done a lot. And actually the joint calibration shows you that you need very large volatility of volatility, okay, very large mean reversions. I put an S because you can have several time scales. And also that correlations are actually plus or minus 1. Okay, that's what happens when you try to calibrate like many of the stochastic volatility models. And of course, if correlations between stoch and vol are plus or minus 1, that actually means that you just have one Brownian motion driving everything, and that's just a path-dependent volatility model. So the reason for it is here the S&P smile, for instance, has a lot of skew, so the slope here is very large. If you increase the square by 1%, you will decrease the vol by 1.5 points for very short maturities. Okay. And this is the VIX smile, okay, for short maturity as well. So what is important here is not so much the positive slope, but actually the fact that around the money, the volatility is around 100%. So it may look large, 100%, but I argue that actually it's small. The reason being, typically, as I said, the short-term skew from the one-factor stochastic volatility model will be minus 1.5, and in those one-factor stochastic volatility model, sorry, in the market it's minus 1.5, and in the model it's always 1/2 times the spot vol correlations times the vol of vol. Okay, the spot vol correlation cannot go below -1. Okay, so if you want to recover this minus 1.5, you need a vol of vol of at least 3. But 3 is 300%. Okay, so 300% is actually like up there, right? It's not at this level here. So of course, okay. So it's a little bit more complicated because you have a mean reversion that comes into play. The VIX is not the instantaneous volatility. So in the end, when you try to calibrate, what you see is that indeed you need to take a very large vol of vol, but also a very large mean reversion. That is for the implied volatility of the VIX to be much smaller than the implied, the instantaneous volatility of the VIX to be less than the instantaneous volatility of the instantaneous volatility, okay, because VIX is an average. So when you mean revert a lot, you have less volatility. But also it selects this -1 spot vol correlation. So I will skip this in the interest of time, but you see here in this experiment with the two-factor Bergomi model, when I jointly calibrate both S&P and VIX term structures of at the money skew and the VIX implied volatility, I get, so here it's just minus 0.99 because that's my numerical bound, but you get, that would be like the -1 spot vol correlation. And actually, by the way, I get vol-of-vols and mean reversions that are much higher than the one that were reported previously, for instance, in Bergomi's book in 2016. Okay, so in the end, what you get is a two-factor Bergomi model, but that's path dependent. Okay, and the two factors actually are Markovian. Okay, because of the exponential convolution kernel. But you see, it's all driven by just the past asset return, but in a complicated way because of this instantaneous variance that is here. That's the equivalent of our AU before. Okay, so also this leads you to path-dependent volatility. There's an information theoretical and financial economics argument, which is that contrary to Stoch-Vol models, the path-dependent volatility models, they do not require extra Brownian motion. Well, just the Brownian motion driving the spot dynamics is enough, and so the models are complete. Okay, derivatives have a unique price that's unambiguous, and all the information that's exchanged by market participants is included in the price, like not just the price today, but all the past prices. Of course, the reality is a little bit more complex, but what we will show is actually that the reality is actually quite close to that. And so it makes a lot of sense to actually start building a model by extracting all the information that past asset prices contain, okay, about volatility, rather than by starting by the other Brownian motion part, like the extra randomness. So we can always add an extra randomness later. And another argument is that path-dependent volatility is generic for option pricing. All stochastic volatility models have an equivalent path-dependent volatility models in the sense that if you that all path-dependent options, not only the vanilla options, okay, they actually return the underlying assets. For instance, think the S&P have the same prices in both models. So you start from a stochastic volatility model like that, for instance. You can build a path-dependent volatility model. That's this one with S hat, okay, such that the distribution of the processes S and S hat are the same. Okay, so because the distribution of the processes are the same, like all path-dependent options on the S&P will have the same price. Okay, and this is the formula, of course, that's probably you would have guessed for those who are familiar with the topic for the path-dependent volatility here. Okay, so it's not a surprise that actually the price, it's the price process S of any stochastic vol or stochastic local volatility model can be exactly reproduced by the path-dependent volatility model. Yeah, so the last argument for path-dependent volatility is this empirical evidence here that we have a lot. I'm just thinking about the rest because this is not the correct slide. So I would ask maybe you guys dealing with the MAG and the PDF. Or maybe if somebody in the organizer can tell them to update the slides that I sent. Yeah, you did it. Okay, that's fine. Thank you so much. Because for now it's okay, but it's going to be more annoying in the second part of the talk. That's literally the slides that I sent at 4:30 a.m. in the morning. Was brilliant. Okay, so you see there's a lot of empirical evidence that the volatility is path dependent. For instance, you just look at the path of the S&P and the VIX. So first you see, okay, volatility, even if the S&P can change from like, 600 here to like more than 4,000 here, volatility stays kind of in the same range, okay? And you see that you have those big spikes in volatility that actually follow like very steep drops in the S&P, okay? So it's always like this, that the volatility reacts and depends on the past. So for instance, you see when you have something like this in the 2008 crisis, or this would be the coronavirus crisis, well, you see that actually there is a memory of the volatility. So even though, for instance, even here, like the S&P goes up very fast after the crisis in March 2020, actually the volatility stays quite high, okay? Because it remembers that there was like a shock in the past. It's not just like the last day, right? That there is a memory about like what happens in the S&P. So there is of course a lot of empirical evidence in the Garch literature. There's also all this literature about time reversal asymmetry in finance. Zumbach and Bouchot and co-authors that basically show that financial time series are not statistically symmetrical when you interchange past and futures. There's the obvious leverage effect, the fact that past returns affect negatively future realized volatility, right? When the S&P is done, then the future volatilities will be up, but not the other way around, of course. So here it's like you have both the asymmetry in time and return R, but there's also more subtle time reversal asymmetry effect, even in absence of arbitrage, which is called the weak zoom back effect, which is that past large-scale realized volatility are more correlated with future small-scale realized volatility than vice versa. Okay, so this can be captured by stochastic volatility model, but is most easily captured by path-dependent volatility. So here you have the time asymmetry, but actually you have the symmetry in the plus or minus return, because it's without regard of whether the market is up or down. And there's this strong zoom back effect also observed, which is defined here in the paper by Jim and Carter. Conditional dynamics of volatility with respect to the past depend not only on past volatility trajectory, but also on the historical price path. Okay, the price, not the volatility. And this can be just restated as the fact that there is some price path dependency in the volatility dynamics. So our machine learning approach will actually confirm those findings and moreover answer those two questions that are fundamental ones. How exactly does volatility depend on past price returns? So trends and squared returns. And also how much of volatility is path dependent. So how much of it is purely endogenous. Okay, and it's going to be a lot. Okay, so we'll explain volatility as an endogenous factor as best as we can empirically. So the objectives are, so first to learn this path dependent volatility empirically, as I just said. So the empirical study, we will consider both implied volatility, for instance, the VIX, and future realized volatility. Okay, so for instance, from 5-minute returns, from not only the S&P, but also other equity indexes. So this will lead to some historical or empirical or PDV model. We will consider like a continuous time Markovian version of that model, and we will show that it generates extremely realistic sample path and also like S&P and VIX miles. And then the next step would be to jointly calibrate this model to S&P and VIX miles. So that would means just input like risk neutral parameters instead of historical parameters. So that would be the implied or risk neutral or Q path dependent volatility model. And of course, what we can also do is account for the small exogenous part by multiplying the path dependent volatility by some stochastic volatility component. Okay, and that would be the path dependent stochastic volatility model. And this is done typically by analyzing the residual, so the true volatility divided by the predicted path dependent volatility. Okay, you will tell me when you want to update or change the slides. Really? Okay, so maybe I'm wrong. Okay, I hope it's going to be okay. Okay, so basically we want to learn this. Okay, so one important step is feature engineering. So try to find the relevant S&P path features that we have to put here in the function f that learns, asset return, that learn volatility from asset return. So we try various models, several parametric forms for f theta. We select the one with the best validation score. We check how the models perform on the test set, of course, that the machine hasn't seen. You see the training, and no, I'm pretty sure that it's not the latest one that I sent, but we'll see. I'm sure actually, but they should. Okay, if you ask again, that would be nice. Thank you so much. And that's a very challenging test set because you see it's just before, during, and in the aftermath of the COVID-19 pandemic. So the test set has very different volatility regimes. Okay, so here we are actually proposing a new simple PDV model that actually performs better than existing competitors as a result of this analysis. Okay, so that's basically the same as before, and that shows you that the path features should be scale invariant, right? It should as we discussed before. So we will consider mostly two types of features. Features that capture a recent trend, okay, and that's in order to learn the leverage effect, whether the trend is up or down, and features that ignore the trend and just consider the activity or volatility, right? And this is in order to learn volatility clustering, okay? Volatility clustering is just the fact, of course, that periods of large volatility tend to be followed by periods of large volatility, and you can also see it in the fact that implied vols tend to be larger when historical volatility is large. So the most important example of trend feature is a weighted sum of past daily returns here. Okay, so you see RTI is just a daily return, and you just like weight it, so it's a moving average, right? And if you weight it with those weights K1, so K1 is just a convolution kernel and typically decreases, right? Because the impact of a given daily return fades away over time. You can also like consider like averages of the negative part of the returns, or even like really positive part, R3, R minus square, something that can capture the trend, okay? Or also like the spot to moving average ratio that is here. So example of features. That's activity features, okay? They ignore the trend, but because here, for instance, they want to take into account the activity, so the past volatility. So here you see we take the square. It's exactly like before, but we take the square of the daily return, right? And we will denote. So here we completely ignore whether it was positive or negative. We just look at the square, and we have another kernel K2, right? And I will denote sigma t just the square root of this thing. So it's actually the K2 weighted historical volatility. Of course, we could consider higher even moments, for instance, of past daily returns as activity features as well. So our model is the following. It's very simple. It says that the volatility, so what is the volatility? It can be implied volatility, for instance, the VIX, or it can be future realized volatility, kind of realized over the next day, right? And it's simply a linear function of R1, so remember that's the moving average of past returns, and sigma t, which is the historical volatility. Okay. And you have a beta 1 that's negative, that's for the leverage effect. You have a beta 2 that's in between 0 and 1 to generate volatility clustering, exactly like in Garch models, if you want. So beta 2 is actually is closer to 1 than to 0. Importantly, both factors are needed. So you need really the trend feature and the volatility features to satisfactorily explain the variation in volatility. And we find actually that this simple linear model does the job, like explaining a large part of the variability observed in the volatility. And you see that it's beyond 90%. So the two kernels K1 and K2 are distinct, and typically, so they both mix short and long memory, but K2 has longer memory than K1. So typically, volatility remembers past volatility shocks longer than it remembers past trends. So here we will consider K1 and K2 with a power law decay, because what the data shows is that the very recent daily returns are given much more weight than the older daily returns. So if you want, the K function would actually start quite high and decrease very fast. Okay, but nevertheless, volatility has a long memory. So the weights, okay, they decrease fast initially, but in the end, they decrease quite slowly.
We have the slides. We can put one moment.
Yeah, okay, that's fine. Thank you so much, David. I appreciate it. It's going to be good. It's the right moment to do it because. So okay, you have those weights K, okay, that tells you how much you should weight the past returns or the past return squares, and they all decrease very fast, okay, and then decrease much more slowly, okay. And one thing that's important is that, so it's very like those power laws, right? But what we find is actually, so what we do is like we do a lasso regression with a lot of just single exponential weights with different characteristic times, right? And so we see that lasso naturally selects a few of them, and when you combine all of them, you get something that looks like a power law indeed, but the shorter time scales are not selected, which means actually that the kernel does not blow up when time goes to 0. There's actually kind of, and so that's why what we use, you tell me when it's ready, when we use, is it a new slide now or not yet? I'm confused. Is it a new slide? Okay. Oh, I need to ask. Okay. So next slide, please. Yeah, perfect. Thank you. And so you see, so what we use actually is actually those time shifted power laws. Okay. So this is just a time shift delta that is here, that guarantees that actually the kernel does not blow up when the lag tau vanishes. And actually, of course, if we force delta to be 0, we recover the power law kernel of rough volatility, but all our empirical tests select a positive delta. Next slide, please. So we then realized that there were similar models in the literature, like the quadratic arch model of Santana from 95, okay, which is very similar. And so you see what the difference is that here is the volatility squared, okay, and the R2 that you see here is actually the generic quadratic form of all path returns, like not just the RTI squared, but all the RTI, RTJ, right? But actually, Schichpartisch and Bouchot in 2014, they have shown that the non-diagonal elements here in this kernel are 1 order of magnitude less than the diagonal elements. So they propose the diagonal Q arch model, which actually reads exactly like very similar to ours, but now here again, it's volatility squared, and this is the sigma squared, if you want, is the R2, not the square root of R2. So we will show that actually our model with volatility and square root of R2 here works actually better, explains better what we observe in the market. Then there's the Ziox process here by Blandoni and Bouchot, where they introduce some quadratic dependence in R1. And there's also the discrete time version of the quadratic graph Heston model of Gadrol, Jusselin, and Rosenbaum. So the version with the θ0 being 0, which is just, you see this parabola in just R1. So there is no dependence in R2 anymore. And there's the discrete time version of the threshold exponentially weighted moving average Heston model by Parent, where it's very similar to this quadratic graph Heston model, but the parabola is only on is one-sided, and the K1 used by Parent is just one single exponential. Next slide, please. So all our model differs in several ways. As I mentioned, it's the volatility instead of the volatility squared. On top of that, we introduce new types of kernels which are capturing non-blowing up power law-like decays. So compared to the last two models in the previous slide, we proved the importance of including the R2 factor or the sigma t. So you need the historical volatility to really well explain the volatility and the future volatility. And compared with M2, which is the one with the R1 square, we actually argue that it's not necessary to include a quadratic factor because the quadratic-like dependence of volatility or variance on R1 is actually already captured by the linear dependence on sigma. That's what we'll see. Next slide, please. Next slide, please. I'm going to skip this. So those are the results on the training set and test set. So on those different indexes here. So S&P and VIX, S&P VIX 90, Euro stocks and V stocks and so on. You see that we get like an error that is just like basically 2 volatility points on the train set and 3 volatility points on the test set. So next slide, please. So that corresponds to train R2. Yeah, you see that are more than 90% on the train set and actually close to 90% on the test set. So just look at the left-hand side because that's the right side for realized volatility. Okay, so you see that we have the different indexes here and the different models that are here. Okay, and our model is the pink one, the most to the right, and you see that it actually gets better train and test R2 than the other models. So you know, of course, when you get close to 1, it's just like 2 increments, but it's all over the spectrum of all indexes. And next slide, please. So this is, for instance, prediction, if you want, or nowcasting of the VIX. On the test set, you see the last 3 years. And what is important here? So the true VIX is in black. The red is our prediction. What is important is that at each point in time, our prediction does not know anything about the past black curve or about the past VIX. The only thing we know is the blue curve. The only thing we know is the past prices of the S&P. Okay, so we don't know anything about the past VIX values. I mean, and it's quite remarkable that just looking at the blue path, we can very well recover the black path. We actually see that this is the coronavirus crisis. We actually see that from our learning, actually the market, the VIX went in the market went down faster than it should have. I mean, based on the model or what the model has learned, and that recently actually the VIX is probably higher than what it should be based on the S&P path and based on our learning. Oh, sorry. Next slide, please. So that's just, okay, showing you like the true VIX versus the predicted VIX. Thank you. Next slide. Next slide, please. Yeah, and that's the residual. So basically predicted versus true VIX around 1. You see, it's like almost Gaussian. And because of this time series analysis here of the residuals, you can see that like a fast mean reversing process around 1 would be a good candidate when you consider path dependent stochastic volatility, multiplying the path dependent vol by a stochastic vol. Next slide, please. Yeah, I should stop. Yeah. Okay. Well, okay. So then I'm going to skip all this. So that's the same for realized volatility. Realized volatility is much more noisy than implied volatility. So of course the R square are less because you cannot recover like the and you don't want to recover the noise in the estimation of realized volatility. So you can, yeah, next slides, please, all the way down. Next, next. Okay. Yeah, showing you. Yeah, so that's basically, yeah, the model here is really telling you, maybe that's visual, is telling you that volatility implied or realized is really like just on that plane here, like in dimension 2, where this is the implied volatility and this moving average of past daily returns, and it's super well explained actually. So it's okay. Next, I will. Okay, next. I will just want to show one thing. Okay, and then I will just do one slide here. Next. Okay, so just when you go, then you can have the continuous time version of it, because the beauty of this is that you just have daily return and daily return squared, right? So it goes very well to continuous time. And you can approximate the power law or time shifted power laws by combination of exponential to build Markovian versions, right, in continuous time of this path-dependent volatility model. The point that I want to make here, and that's the novelty of this model compared to, for instance, James' model, Raphael's model, is the inclusion of this R2 term that is here. That's the past volatility that only creates a drift term in the model, but that's a very important drift term. And I will be happy to show you the slides during the reception, of course, because everybody will want to see the slides during the reception. I know you. And then you'll see that this model generates actually, generates like very realistic path for both the S&P, the VIX, internal volatility, real volatility, and also for the smiles of the VIX and the S&P.
Which is fascinating.
I stop here.
Fascinating. I suggest perhaps a special presentation for those who wish to attend after everything is open during.
I'll be here. Yeah.
Probably not after we do it.
So anyway, thanks a lot, Julien.
Thank you very much, everyone.
We got to go to the next speaker, who is going